So this chapter first looks at just how does a CPU work with main memory. We're not going to cover virtual memory at this point in time, although there's going to be many hints about how virtual memory works in this chapter already. And there's certain sections in this chapter that's very practical again, so we're going to do some nice calculations again and see how it works and so forth. But there's also obviously a lot of theory that you have to understand. Now, one of the first things that we have to understand is when we think about a program that runs, there's obviously, and this is kind of was one of the questions that was included in the semester test, was what happens when you run a program? How does it influence the storage hierarchies in your computer? Before you can run a program, meaning before it can become a process, you have to load it into the memory of your computer. So that means that if it's loaded and it's stored there. The main memory and the registers are only storage the CPU can access directly. You cannot directly go to the hard disk and access stuff from there directly, even if it's an SSD. So even though an SSD is kind of like main memory, but some of them are really becoming as fast as main memory, the architectures of today's computers still require main memory and the registers are under caches. So those are the only things that we can access directly to execute stuff from, and basically access them from. The reason is that your main memory gets divided into addresses. Right, so let me see if I can demonstrate. You must have seen this before you use the debugger. So debugger quickly here. Go to the process, open it. I'll zoom in just now. Let's take this. Right, so the first thing, again, let's run the code. That numbers you see on the side, that's hexadecimal for an address. Now, what's the difference between that address and that address? You see there's a F0 to F5. There's basically, what is it? 0, 1, 2, 3, 4. There's 5 memory addresses in between those things. So that should tell you something a little bit about this instruction. Certain instructions takes up, for instance, call mmap, blah, blah, blah. That takes up 5 bytes, because each byte is mapped to a specific address. So this instruction itself is 5 bytes. One is the actual opcode for the call, and the other one is probably a memory address from where it's going to call that function. And that's why it takes up 5 bytes, and it makes sense. So the call is 1 byte, and the parameter of where it's going to, remember this is a 32-bit architecture, so each word is 4 bytes inside. So 1, 2, 3, 4. That means it takes 5 bytes for this full instruction to execute. The next instruction is 5, and then goes 8. That's also quite a significant amount of the loss. So 5, let's just jump in there. Let's have a look at some more individual. Go. So here we've got, for instance, remove ECX. This one takes up, 6 bytes. Can you see there? Between E00102 and E00108. So what I want you to realize is that each instruction has a specific address in memory that we access. Now a little bit of a hint of something in the future that we're going to talk about next week, or in the next chapter, is if you look at the memory map. This memory is actually, the user code itself is living inside that memory address right there. D4 1000 and up to the size of C4000. So that's the size of the code of the specific application. Then obviously we've got some data segments and so on and so on. That's not that important. But what is interesting is if I can run the second application, maybe I should try and do that. Let's see if I can put the second instance of the debugger. I'm not sure if it's going to allow me. Yeah, it will. Good. Let's see if we can open another process. And this guy, okay, so memory is a little bit different. So this one uses memory, what is it, 400,000. And the other one, let's see if we look at the 400,000. There was something, there's nothing. This one is not a very nice example. But effectively, if you look at these memory maps, these memory addresses, they actually overlap. How is it possible? How is it possible that one application can have an instruction in a memory address and another process can have an instruction in exactly the same memory address? Okay, we'll discuss that in the next chapter. But what we want to first show you here is that each instruction and data must be loaded in the memory of the computer, and we basically access it by using these addresses. Now, what register again stores the address of the next instruction? Yeah?
Yeah, the instruction pointer.
The instruction pointer. The generic name used in the textbook is the program counter. So on the x86 processor, it's EIP, the instruction pointer, but in it's the generic name for it is the program counter. Just remember that. That is typically the, and again that should show you that we're accessing an address. Now the question is, how is it possible that we can run multiple, stop this, how is it possible that we can run multiple processes in the system and they still, all of them basically can work in the same memory? And for that, you'll see that there's certain hardware in your computer that helps with that management. This, to see if there's anything else. Obviously, a memory unit only sees a stream of addresses, read requests or addresses, or address for data and write requests. So that's basically what happens inside the CPU. You get what we call a memory unit, and that basically doesn't really matter whether it's code or data, it stores in there, or reads from there, or updates there. Register access is one CPU clock or less to access something in the register, but your main memory can take many cycles. Okay? So accessing stuff from main memory is extremely slow. So that's typically, think of this as you wanting to fetch something from the library, an instruction from the library, have to walk all the way to the library, get back here and pass it, and that is the instruction that you're going to take. So that's why we use something like a cache, and the cache sits between the main memory and the CPU register, so it will fetch us a number of instructions ahead, or a data structure, like a block, and put that in the cache of the memory, which will make it significantly faster. There's also the principle of memory protection. Certain types of memory, we want to make sure that we can only execute instructions from it. Or we want to make sure that that memory is only able to use for data. Meaning we can write data in there or read data from there, but we don't want to execute it. That's typically what malware tries to change. Now, to help us run multiple processes inside